started. Today, Che is going to tell us about supersymmetry and superspace and stuff. You give more details.
Okay. Yeah. Yeah, so today we are going to talk about supersymmetric signal models, and we are going to construct it via superspace. So before talking about supersymmetry, let me start with some general things about field theories, or field theory, or more explicitly, what we are talking about should be called the Lagrangian field theory. Yeah, so when we talk about this, we basically need two pieces of data. One is the field, and the other is the Lagrangian. So yeah, so we pick some space type. Let's call it MC, which is going to be which is going to have the Minkowski signature, and so field they are just fields are like functions on your space time. So usually we denote them by phi x, psi x, whatever, and Lagrangians are functions of fields. So, for example, you can take L, maybe the partial derivative of phi, and then minus some phi square term, minus some phi fourth term. Yeah, and so if you're so there's classical field theory and quantum field theory. If you're doing classical field theory, you want to so you define your action F to be the integration over all space time of L. This is for the action. And you want to look at phi so that the variation of F equals 0. This will give you some function of phi, which is usually called equation of motion. And if you are doing quantum field theory, so you're going to say we look at the so-called partition function, which is the integration over all possible fields, and the e to the minus I s, where s is your action. Yeah. So of course these examples I only have one field, but you can have more fields. Let's say you have phi 1 all the way up to phi n. And your Lagrangian can also be constructed out of these fields. For example, let's say you take yeah, you can take some Lagrangian of this field. And so now you see, instead of viewing them as separate functions, you can see that you can say that these fields they give you a map from M to R to the N. And now if you can also say my target space is not necessarily always R to the n. I can replace it with some more general manifold, and then you will come up with the definition of sigma models. So yeah, so what's a sigma model? Even a Riemannian manifold. Let's say X with a matrix G, and also a function. So we have a function which goes from X to real numbers, and this is usually for the potential function. So the field, yeah, sigma model, that are next phi from your space time to this manifold, and I also need to specify the Lagrange, which is going to be so let's say first you have an analog of this kinetic term which contains derivatives and also a potential term. Yeah, and so this term here. So this term here, it's where you use the Riemannian metric. So in local coordinates, this is Gij of phi, and I'll show you. And yeah, you see it's a direct analog of terms like this. Yeah. So I should say that I think in physics literature, the definition of sigma models is usually people don't have an exact definition, but whenever you have some Riemannian manifold that we will consider maps into that manifold, people call it a sigma model. But yeah, so I'll say this is a basic version of the definition. And later we will see we will add we'll add more fields that's kind of related to phi. Yeah. So one more thing about this sigma model, I will go on here. So we need to define what's called the moduli of vecua, which will be relevant to us next time. So assume V is bounded below. So we define moduli of vecua. So we call it M stack. It's going to be the place where V gets its minimums. V of minimum of V. And so maybe one remark. Why do we call things like this the vecua? So given a Lagrangian, there is a way to determine the function, the energy of a field, and it turns out that the fields that attain minimum energy are fields that has constant value in this space. So let's do it. are constant by energy or equal to some constant value inside that. Yeah. So, okay, as the most basic example, if we just take x equals r with the usual metric on it, and so and we get back to our L, which is I guess I'll call it star.
When you say fields giving minimum energy, does it mean minimum action?
No,
or is that
no, so usually the Lagrangian is kinetic energy minus the potential energy, and in and in this case the energy that we want to minimize is kinetic energy plus potential energy.
So the field's minimizing the integral of 1/2 d phi squared minus plus phi pullback of phi of v.
Yeah, right. Okay. Yeah. So let's put this part, and yeah, and let's say L is star. Yeah. So this energy is so there's something called Noether theorem, which says that for every symmetry there will associate with it there are some conserved quantity, and energy is the thing that is associated with the time translation.
Wait, so if x equals r, wouldn't it be the first Lagrangian you wrote down?
The second one for n equals 1.
Yeah.
Oh, this yeah, that's correct, exactly. Right. Oh. Sorry. Yeah, I don't mean to say it in that very first. Yeah. Thank you. And so if we want to study what's the model of vacuum, so this is going to be yeah, I guess there are two cases. So first we assume that V has a minimum. So alpha is always greater than 0. But depending on whether lambda is greater than 0 or smaller than 0, your functions, this is B, this is your value of phi, will be either like this, where your minimum is just a point, or it will be like this. So your minimum is 2 points. Yeah, I guess that's a quick introduction of signal model.
Why shouldn't we be varying alpha? Then we want lambda to always. Oh,
So here this alpha and lambda, there are some constants.
But we always want lambda positive so that the potential goes to infinity at infinity, right?
Yeah, you're right. Sorry. So you want lambda to be greater than 0, but then depending on your whether the quadratic term is positive or negative. yeah, so now we can get back to supersymmetry, and so we have so we define sigma model, and we want to define some sigma model that actually has supersymmetry. So yeah, for this we are going to have a toy example, which is a superparticle on M1. Which is in this case it's the real line. So to begin with, recall some facts from our last two talks. So we define the super Poincare algebra. P in general, in d-dimensional spacetime, it's going to be equal to this spacetime translation plus spacetime rotation and plus S, where S is a real representation of the spin group. And we will specify the anti-commutator of things in S2 should live in space-time translations, which is actually given by yeah. So but now we're in one-dimensional space-time. So this simplifies drastically. This is one-dimensional, no rotations, and for S we will take it also to be one-dimensional. So in our case we have P, I'll call it P1/1, which is going to be a direct sum of R and S2. And so for this R, the generator is time translation by T, and for this S2, I would call the generator Q. And we want the relation anti-commutator of Q to be equal to two times the derivative in T.
So there's no spatial dimensions. No.
Right. Just S is yeah, that's correct. Okay, so yeah, so now we actually want to write down a single model that has supersymmetry like this. So fix a Riemann manifold X. So first we will have phi. But at the same time, we will also have a phi. So yeah. Now this is the first time I need to relax the notion of sigma models a little bit. We want this psi to be a section of phi pullback of parity reverse of tangent bundle of X. Yeah, and so usually people call phi to be a Bosonic theory, and this psi to be fermionic, because it lives in some odd direction. And we write down some Lagrangian. So usually physicists will say a Lagrangian should start with the kinetic term, and for Bosonic field, the kinetic term is something like this, and plus the plus the fermionic term, which comes from the psi and the time derivative of the psi.
Can you explain what I don't understand what psi pullback compared to here? What kind of object is I don't understand that. So you wrote this thing.
Yeah. So you can first forget about this parity reversal. So it's it's some the tangent bundle on X, and you point back to your space time, which is just M1.
Okay.
And
in two-dimensional vector one.
it's the dimension is the same as X. Sorry. Yeah. So the bundle itself, this is tangent bundle of X.
Yeah.
So the dimension of the bundle is the dimension of X, but you want to take a section of that bundle. And this parity reverse, I think we just deal with it formally. That like it just tells you that this lives in the odd direction. So when you have like when you have some two odd things multiplied together and you want to switch them, you need to get a minus sign. I think that's basically the parity tells us.
Is that the pi symbol or something?
Oh yeah, this is supposed to be a pi.
Standard parity?
Maybe.
Yeah, I can't really, in general, multiply two sections of the vector.
Here, yeah, you're right. So we're on Riemannian manifold. So you have a metric on your tangent bundle.
Okay.
Yeah. Oh, so sorry. Okay, yeah, I see.
No, okay.
Yeah, and also this derivative will be a little tricky because it's the covariant derivative, not the naive derivative.
Can you explain again what the pi does?
Uh,
is mathematical.
So I was thinking a curve, okay, but X can be any or minus. So I read that as Riemann surface, my bad.
sorry.
I just want to add, you can multiply them. It's just that you just take it to limit like exterior algebra over the original vector. Okay, that's the only thing. So even without metric, you can still multiply. You just have to interpret it super. Okay.
Is there like some standard even odd structure in TS?
So when I just I think about that, they all.
Yeah, it's really even, I think, right?
Yeah, right.
Oh, so it's purely even, and you're just, when you put that in there, you're just thinking of it as odd?
Yeah, right.
So like the fibers are like purely odd vector spaces, basically.
So, but we're not thinking of it as just the degree one part of the exterior algebra of Tx, because that would be odd, right? And then we would know how to multiply them together.
This is like a super vector bundle or something, like pi tx.
Yeah.
Well, look,
Yeah. So I guess we touched. So we briefly talked about this thing. Like if you have some R maybe M/N, you can view this as a rank. So first, if you have R plus N, you can view it as a R bundle on Rm. And so we'll talk about this. You look, this is the parity reverse of this Rm bundle on Rm. And if you want to say like mathematically, how do you define this? You define it via the ring of functions. So the ring of functions here. It's going to be the real functions Rm tensor with the exterior power of Rm. Yeah, and so yeah, let's see.
So in
Yes,
this-
yeah,
I think what's going on is that there's, what we're doing is we start with a function from R1 type 1, so 1, superspace, which has the functions that describes. We're not looking at just the smooth functions, we're looking at maps from that into M. Into X. And then the idea is we can represent basically, so we have this supersymmetric map into X, but we can represent that map as in component fields that are basically saying we're going to split apart the supersymmetry and just think about them as just functions. We're just going to write down the functions in components on space-time. So we have the sort of real component, which is just the ordinary component, which is just the bosonic part, just a map to X. And then we have the fermionic component, which in this case kind of captures the, I guess you can think of the superspace as like an infinitesimal tangent bundle. That's kind of how it transforms. It transforms as derivations. The odd part of the tangent bundle transforms as derivations. So I guess that when you look at maps from superspace into a manifold, when you write that in components, the odd part looks like essentially a vector field on your target manifold.
So the idea is
Yeah.
we should be thinking like maps from R1 step 1 to X.
This is another way of writing a map from R1 type 1 to
Yeah,
X.
okay.
This is writing that in components. Yeah.
yeah, okay, yeah, that's where we are heading, okay. So, yeah, okay, I think we have done this, and, so for now, for now, we're still on the usual space time. We haven't touched the super space or super field yet. But for now, we have this model, and we just write down a supersymmetry by hand. Let's say eta is some odd parameter. And so you define an infinitesimal translation of your field. So I want delta phi to be eta of the psi, and I want delta of the psi to be eta of phi dot. And you can check that when you do this change, how will your Lagrangian changes? So yeah, for simplicity, let's say we are like our Riemannian manifold is flat, so that we don't get a lot of curvature terms or whatever. So the thing you'll get is, so from this d phi you get something like phi dot times psi dot. So minus eta to psi dot and phi dot. Tell them, and yeah, for the second term, you either you vary this or you vary this, so you will get eta phi dot psi dot. Also I eta phi double dot, and both things. And if you follow the rules that when you exchange two odd variables, you are going to pick up minus sign. You will see that this is actually equal to minus a half eta phi dot phi dot. Which is going to be a total derivative. And of course, we multiply a total, integrate a total derivative on the whole real line, and with the usual physics assumption that your fields will fall fast enough at infinity, so this thing will be zero. So integrate dot L. Yeah. So basically, what I have said is that I have this model. If I verify it, so if I verify it in this way, then your Lagrangian don't change. In other words, this is a symmetry of our model.
So when
And
you say eta is an odd parameter, you mean it's like a section of the pullback of the parity reverse tangent bundle, or?
I think in this case, so most of the odd things we are dealing with it like in a very formal way. You just think of it as if you have a usual symmetry, what you do is you have a very small parameter epsilon, which is you think of it as a small real number. But for supersymmetry, the symmetry itself is odd. So you need to multiply by some odd parameters so that they can actually act on fields.
So but eta is just an odd scalar. Is that the thing?
That's how I think about it.
Okay.
So yeah, so we have this delta, this infinitesimal change, and we want sure.
Yeah, could you make the dots a little bolder, just?
Yeah, I can't.
Oh.
Tough dots.
Thanks.
And on the left, so that's like your equation of motion, or like when you introduce the eta.
No, we're not using equation of motion. Like so this thing it holds for all psi and phi and psi. I guess these are two dots. Okay, I guess I'll write partial t instead of dots, and that might be better. So we want to identify this delta with our supersymmetry generator Q. So we have one more thing to check, which is the commutator of delta. For this so if like Q is the odd generator. Well, what this means is that either Q is the generator of delta. So if we have two odd parameters, either 1Q and either 2Q, and you act on phi, so what will we get? So yeah, we can do a quick calculation. If you act on phi, you get either 1 times psi, and when you act on it again, you times either 2 and you get phi dot. So what you finally get is minus either 1, either 2, phi dot. And you can do a similar calculation of how they act on the fermionic field, and you will see basically the same thing. So what this is that if you factor out these okay, there's a factor of 2. If you factor out this either 1 and either 2, considering the fact that you are going to reach this either 2 pass over this Q, we see that the anti-commutator of Q is equal to 2 times partial T, and this is what we want. I guess I will continue on that. Okay, yeah. So we finally get to superspace formulation. So instead of the usual space time, we want M1/1, which is going to have one even direction and one odd direction. So this is still the parity reverse, and I'm going to call the coordinate here t and the coordinate here theta. So there is an inclusion map from the usual space-time into your super space-time. And if you pull back along this, it's basically your set theta to 0. So okay, now let's say we have a field big phi, which goes from M11 to X. So this is what we talked about last time. This was super field. And what we are going to do is
Here,
Sure.
or data, like, even parameters or something?
no, it is odd.
It is odd and Q is odd?
Yeah,
Wait, what does it mean that Q is like a generator? And like Ada's,
oh yeah,
is Ada also a generator or something?
no, it is always a small parameter. You just imagine in the usual case, usual even case, that you have a very small real number that you multiply to some generator. So you have some, yeah, that's the usual way you write some small variation.
Or it's Q, the Q is odd
Yeah,
and P is even. And Q times phi is like odd. Or
so that's why we need this theta. So you want to keep things even. So that for example, you want to change this phi, you want to change it by some even things. But the phi is going to be odd, so you need to multiply by some other small odd parameter. I guess I'll go. There will be more examples, and it will be clear how we deal with these odd parameters. But yeah, because we have this super space time, and yeah.
why is Q odd if Q acting on an even thing? If something is even.
So
Or is it not?
th-
If it's Q phi.
that's why I need eta times q to act on the even thing instead of just q.
The formula he wrote for delta is really eta q.
Yeah.
And
So yeah.
I should.
Oh.
Okay, fine.
Yeah, sure.
You can formulate the whole thing with odd differentials. It's not really a problem. I mean, the odd parameter stuff is just kind of, I don't know, convention in physics literature. Like for example, in this actual example, if you had M1 as S1, and you just drop eta, and delta would literally just be, so I mean, okay, you can think about loop space of X, and this would just be like equivariant de Rham differential on the loop space. It's okay to have the odd derivatives. But for some reason in a bunch of physics literature, we're addicted to this thing.
Okay. Okay, so sounds like it's unfortunate that we have this odd parameter.
I mean, it's just both ways work. It's just which minus signs you keep track of.
So when you say phi is a map from M11 to X, are we viewing X as a super manifold in some?
No, so X. Oh yeah, so X itself is purely even. But we are so we are viewing it as a super manifold, so that we have a map in this way, and the most correct way to understand this kind of map is to understand how the function of rings changes in the reverse direction. Yeah, I guess for my talk, I haven't go into many details about the super geometry. So usually the geometric picture I have in mind is that so first if you have M let me write here. So if you have M01 map into X, so the picture is that if this is your X, this map is specifying a point plus a tangent direction. And this you can explicitly see from the the map of ring of functions. And now what you have from M11 to X, what you specify is just a curve plus a vector field along this curve, or
So
yeah.
we're viewing X as a supermanifold with its algebra of functions being like C infinity of X tensor these like the exterior algebra of X.
It is not tensor anything. It's just
No.
the
No.
infinity of X.
Okay.
It's a purely even supermanifold.
But so we can have maps from purely odd supermanifolds into purely even supermanifolds. That's
You can change the degree.
Okay.
Like the degree can change. So when you map to here, you basically you get two parts, the odd part and the even part. And the odd part tells you the point. The even part tells you the point. The odd part tells you the tangent. Yeah. Or in other words, this phi is it really contains the information of this phi and phi. And so yeah.
So can you say what happened on 0 and
So
like you do this picture, it's like a point and a tangent vector?
yeah, that's correct.
Okay.
So you can think of if you oh okay yeah it's so what we are going to do so we want to construct some Lagrangians on the usual space-time, but instead we can construct we first construct something on the super space-time. Let's call it curly L, which is a function of big phi. M11. Such that its integration over the whole superspace is invariant. This is really not so hard because you already have the superspace, you have the superpunctuary acting on it. And with this, then you can define your street L to be the integration over the theta of the curly L. And and of course this implies that when you integrate this L over dt is invariant. This is the first point. And the second point is that you have this superfield, but you somehow need a way to recover this write this superfield in terms of the usual field you have. So maybe second is that the way you do it is that you somehow do a Taylor expansion. In the odd direction. And yeah, so I guess Elliot just said it. Okay.
Sorry, I didn't catch. What did you mean by invariant again?
So what do I mean by invariant? Oh, okay. It's like invariant under the supersymmetry.
Ah.
So yeah, because now your supersymmetry algebra will act on your space-time, which will induce an action on your Lagrangian. And yeah, invariant just says this integration doesn't change. We're going to do this Taylor expansion, and theta is odd, so you actually only get to order one of theta. So in principle, you can write something like with capital phi is equal to some phi plus theta of some phi. So this is okay in this case, but in general, it's a more invariant way to do this. For that, we'll introduce some vector fields on your super space-time. So I guess there are some useful vector fields. M1/1. So first you have partial t, and second you have b, which is partial theta minus theta times partial t, and you have q. I'm abused the notation a little bit because q is supposed to be the generator of the superpunctuate algebra. But we will also specify how it acts on the superspace.
Sure, when you say invariant, you mean like with respect to Q or something?
Right. So with respect to Q and the space-time translation, and also rotation if you're in higher dimension. So remember whatever in the superpunctuate algebra can act on your superspace.
When you say invariant here, it means with respect to everything in the superpunctuate?
Yeah, that's correct. Yeah, that's what it means for you to have the supersymmetry. So, and I guess it's useful to write down how these vector fields commute to each other. So we'll have the commutator of D is going to be -2 partial T, and the commutator of Q is to be plus, yeah, and D and Q commute, and partial T commutes with everything. So yeah, so continuing this, so a better way to do this is to say that phi is equal to I star pullback of this phi. Remember our I is the inclusion of usual space-time to super space-time, and you also get phi, which is I star of T acting on phi. You can see in this case it's you really get what you have in the Taylor extension, because the D differ by the usual partial theta only by a theta term, which will be killed by I star. Yeah. So I guess now we can write down our Lagrangian, which is going to be 1/2 minus 1/2 of the pairing between d phi and the partial.
So when you're at commutator, does it really mean commutator?
It's the out commutator. Yeah, sorry, yeah. Thanks for asking. I should say this. So partial t is given, and these two are odd. Yeah. And when I write this, it means like commutator are up to the degree of the
super.
yes, right. So you have this, and if we integrate it over d theta, so yeah, this integration we will use it many times. So the basic rule is to integrate d theta of a plus theta. This is going to be just b. Like the integrated number is going to be 0. Integrated something times theta, you get that something. So if you carry out this integration, you'll see that this part from our definition is going to be minus theta of the derivative of phi plus phi. And this part is going to be the derivative of phi plus theta times the derivative of phi. And you see that we will do this integration. You just get back to your usual Lagrangian. Okay, and yeah, and you can see this. So this L will integrate over superspace time. It's invariant under Q because Q commute with D and partial T. So we act on phi with Q. It just come out, and when you integrate it becomes 0. So yeah, and then that tells you that the Lagrangian, the usual Lagrangian we constructed here, is also invariant under the translation of Q. So I guess.
So now that we've
sorry.
constructed the nice invariant Lagrangian, is it a good stopping point to go do T stuff?
Yeah. I guess I'll just very quickly summarize what we have done. So what I have said using the what I've said using superspace is usually called superspace formulation, and what I've done is to translate this into the so-called component formulation.
Just one quick question. Should we be thinking of curly L as like some kind of Lagrangian density?
Yeah, the correct name is Lagrangian density, and we'll integrate it.
Okay.
That's really what they call it. And I describe a way to go from here to here, and usually it's hard to go back. So you have superspace, you translate it to the usual space. You have superfield, you extend it into the usual field, and so you have your supercharge acting on this phi, and you actually have a way to parse what's the action on the usual field of phi and psi, and lastly this Lagrangian you write it as a usual Lagrangian, and that's how we usually use superspace to cook up a supersymmetric theory in the usual space time. And after the T, we will look at some examples in dimension 3, which will be a little more complicated. I guess, yeah.
Well then, I guess we will reconvene in approximately 25-ish minutes.
Oh, okay, yeah. So we continue our discussion. And now we are in 3-dimensional space-time. So again, let's begin by to recall our superpunctuary group. So first, if you look at this one, what we have been discussed for the last 2 weeks, it is the isomorphic to SL2R. And so what we are going to do is we let S to be the fundamental representation of SL2R. So the figure is 2-dimensional. And we will also have a map gamma, which goes from the symmetric product of S2 to B, where here B is just R12. So we will tell you the anti-commutator of things in S star. So here are superpunctuary groups P32. yeah, so when I write notation like this, the second one means the number of supercharges. So it's different from this by a number of two. So we have translations and equations and S2. So we also perform our super space-time, which is basically the same thing without rotations. And yeah, I should say these things are in the even part of the D algebra, and this is in the odd part of the D algebra. And also we have even dimension, odd dimension, and I'll give them some coordinates. Let's call things here θ1 and θ2. And so since we already have this isomorphism, I will use it to define the coordinates on B, which I'll call it y11, y12, and y22. So, and of course, the relation is that if you have θA tensor and θB here, it should go to YAB inside B. So, and as usual, we will write out the differential operators. So the partial is just space-time translation. A and B is 1 or 2. And yeah, so we recall that this is totally parallel to the one-dimensional case. So BA is going to be you take derivative of theta in derivative of θA minus theta B partial AB, where B is sum here. And also you want to define your supersymmetry generator to be the same thing with the plus sign. And yeah, and I'll write the relations here. So if you commute BA and BB, this is going to be -2 times partial AB, and of course BA and Q commute with each other. So we will do what I have just done for the one-dimensional case, namely, if this I is the inclusion from the usual space-time into our super space-time, and phi is a super field, so a map from a map to a target manifold. So yeah, so X is to a Riemannian manifold. So we define phi, which is I star of phi, and phi is I star of A star, and also that, which is going to be so it's going to have two derivatives, but you also want it to be somewhat symmetric, so it will be two derivatives, but they will be contracted by a sign here. So this is either 1 or -1 or 0. So yeah, and we do our usual trick to define the Lagrangian. And so the invariance of L follows from the same reason as the one-dimensional case. Basically, the Q will commute with B, so it gets all the way out. So if we integrate this over theta, we will see that this will give you the usual kinetic term. And since we are on general Riemannian manifold, there will come out some curvature terms, which is it's kind of boring, but I'll just write it down. And plus the term involving F. So so the D here is it's usually called the Dirac operator, which in which in terms of indices, it means it means this, which looks a little complicated, but a more familiar way you will see this is to say that d slash psi equals gamma mu partial mu psi, where in this case mu is 0, 1, 2, and gamma mu satisfies Clifford relation. And as we have seen two weeks ago.
So R is the curvature on
M? Yes, on X. So X is our Riemannian manifold.
And so there we're using that somehow psi ends up being the same as a tangent vector.
Oh, right. So strictly speaking, this thing, this psi, will give seen So basically, the phi itself is an actual map, and every other thing will live in the tangent bundle.
Wait, when we say phi, capital Phi.
Oh, no. I mean, okay. We'll get small phi. So it's a section of I guess pullback of the parity reverse of the tangent bundle tensor with S. Because now you have your index has 1, 2, so it's actually two-dimensional. And if you look at how they transform from the same as S.
Okay, so then the psi. Oh wait, okay, so the pullback of Tx, I see how I can plug that into the curvature tensor, but what about this S?
You forgot. So this is just telling you that it's two-dimensional. So I write S because it also tells you how it transform under SL2R.
Oh right, so the S indices are the ones that we're contracting with the epsilon. Okay.
Yeah, you're right.
Okay, I see.
So are the epsilon AB playing the role of our gamma matrices essentially?
Epsilon?
Or the
No, this epsilon are I guess no. These epsilon are really like delta functions, except that now what you want is like sometimes it's 1, sometimes it's -1, and sometimes 0.
Well, the answer is kind of yes and no. I mean, like you can pick a basis of like you pick like explicit representation of gamma matrices such that one of them will be like S. But in general, it's just an invariant of SL2R.
Well, I guess I'm just confused because you wrote that it's equal to the gamma matrix conjunction with the.
Oh, so there's an implicit change of basis here because so the coordinate I use this y11, y12, y22.
Mhm.
So if you compare it to the usual coordinates,
Okay.
so because like on this space, so you already have x0, x1, x2, and so this is this one here, and so they have a if you want to transform this into things like this, it will tell you that I guess it's something like. So if you make this change of basis, you really get the standard Clifford like direct gamma matrices. It is maybe so things like this. But in this coordinate, they looks kind of different. For example, this one maybe look at 0, 1, 0, 0, and 0, 1, 0. This is. Yeah, I tried this yesterday. So they specify the Clifford relation under the metric on this y coordinate. Yeah. So yeah, I guess the answer is if you. Okay, I guess the answer is yes. This absolutely plays a role of gamma matrices.
Okay, and so we need this particular form for the y's so that so if we had y be any coordinates, then we would have to have terms with the metric on v appearing in the Lagrangian, but you pick like particular y's and then these metric terms just end up somehow becoming epsilons and stuff.
So the thing is, if you think of this epsilon, there are really 2 by 2 matrices.
Yeah.
That telling you how this partial is going to contribute to this d/phi. If you change the basis, you just change this matrix.
Okay. Yeah. Okay. Yeah.
The gamma is just a spin representation. Nothing to do with the metric.
Wait.
No, I mean that's not like the y's. The only role of y's is just it's a concrete way to realize that the second symmetric power of the defining representation of SL4y is the same one that the x is transplant. And then you're just picking some coordinate that makes this clear so that you can write everything in terms of what's there in that. Yeah.
What is the comma in phi Dirac phi? Or sorry, psi Dirac psi?
So you're taking an inner product because you are on the Riemannian manifold. So,
Or like, is there supposed to be a comma here?
maybe there should be something here. I think
Also, what is R? Is it
it's the curvature.
like scalar curvature or something?
It's the
Wait, what is the acting on?
okay. I think it's like covariant derivative C and covariant derivative E in this case. Like these are it's like it takes 2 vectors and becomes an endomorphism of vectors.
Oh, okay. And then that acts on psi G.
Yeah.
Okay.
I guess yeah. Don't worry about it for now.
Explicitly has 4 ends.
Oh yeah. So okay yeah. So maybe I'll make a few remarks about this example. Yeah. So first, if you look at these things here, so this is usually called a scalar multiplier. because you can imagine when you have supersymmetry, it will change bosons into fermions. So your field they also comes in families, and these families they are usually called multiplied. And in our case, since we start with something that looks like a scalar, people call it scalar multiplied. Yeah, that's remark one. And remark
So, what exactly is scalar multiplet? Is it all of those fields?
yeah, the collection of these fields by yeah. Oh, I guess the F is a little tricky here, which is my next comment. So what you'll see is that F appears in L only algebraically, meaning it has no derivative. So this means that we can actually eliminate F using the equation of motion. Depending, yeah. For example, in our case, we actually have F equals 0, so it doesn't do anything. But sometimes you will see something like F squared plus F times some other field, and when you take its minimum, you have F equals minus that other field. Okay. Yeah. And second, so we have said we have bosonic fields and fermionic fields, but for our later analysis, we will actually focus on bosonic fields. In other words, we will use the bosonic Lagrangian. Which is defined as setting all fermions to 0. Which in our case is it's kind of boring. It's 1/2 d² squared. So the bosonic Lagrangian is what we will use when we analyze the moduli of vacuum. And yeah, next time we will see more interesting structures in moduli of vacuum. Okay, what's the time?
Oh, it's
Should I?
3:57.
Okay. So, oh yeah. So I guess I'll use the last 3 minutes to make some general comments about 4 and 6 dimensions, which we will use next time. So if you look at dimension D, so we have considered 3, and next time we will also see 4 and 6. So if you look at this C1 and D-1, in 3 dimensions it's SL2R. In 4 dimensions it's going to be SL2C. In 6 dimensions it's going to be SL2H. This is quaternions. And
special linear, like how do you take the determinant of a quaternionic matrix?
I guess it can still do
I thought like it matters in which order.
Oh.
Like since it's not commutative, somehow it's not clear. Which...
The way it goes is I mean, I won't say the answer in general, but I'll say for checking that the actions are actually supersymmetric, you never actually need to worry about this. For example, in 8 you can do SL2O, and you never have to use it. It's not associated. So it's always a little like. Do you just mean definition of group SL2H?
Yeah, like is the determinant somewhat multiplicative for quaternions? I guess is,
Maybe if you choose the order correctly.
okay, maybe there's some way.
It's here to just take the Lie algebra and then
Yeah,
just
yeah.
exponentiate it.
That, I guess.
Yeah, just do that way. Don't think about the group by like a determinant of.
Wait, I mean, is the, okay. I mean, is the Lie algebra is the commutator of two trace zero quaternionic matrices and trace zero.
Oh,
Like I think that also is commutativity of scalars.
okay, cool. Yeah, I can yeah. Oh, yeah, so, and then what do you care about, the definition of minimal real representation? Yes. So, in this case, we have since 2, and in this case, it's actually 4, which is just the fundamental complex representation, complex 2-dimensional, real 4-dimensional, and in this case, it's 8. So we know that this number actually determines the minimal number of supercharges that you could have. And so next time we'll see supersymmetry 4 and 8 supercharges. And yeah, I guess that's it for today.
6 is more than 4 just like, if I take same 2 of this thing, I think that makes something that matches that, you know.
Which one doesn't match?
Shouldn't like same 2 of this representation be?
It's not always true. So what you really need is you need to have a map from yeah, it's just a map, not always.
In fact, this is kind of distinguishing characteristic I mentioned for you, is that this is actually an isomorphism. But that's not true anywhere else.
Well, in fact, it just automatically because the spin representations for like two to the something and these are
So next week, Che will continue and talk about hyperkähler stuff, finally. And then at that point, we'll be ready and steady to actually talk about Coloumb branches, because we can just say, oh, it's a vacuum moduli space, and then we get that it's hyperkähler automatically from supersymmetry. And then we're off to the races. So let's stop the recording.